So I'm slightly changing title. So before getting to these outlaws, we will do some more that thing. So this kind of the one where all the laws are kept. So this are formula like this. More here, 96. Say that if, let's say, x as thermostat 597, that means then we can characterize when it has a coarse multiface. So there exists a coarse multispace if and only if the inertia is finite. And the nice thing with this might mean different things for you, but I'm going to apply it properly. Able to project it. And in addition, also it has like same functions as my stack. So this is the ideal case, but we'll see this everything that I mentioned. Think of these three actors will all be breaking these laws, and perhaps just to see an example where this is not satisfied. Example is to take a non-separated A1 and divide out by each of the elements. So this gives me something that looks like A1, but you will have some staticness except for the origin. This does not have high dimension. And we're going to have a slightly different perspective is where you say it's unpunctured. And this is an example of punctured inertia. So the inertia here looks like it has the identical components, and then it has this. The one component of here is the function. I may say that the whole is approach. Coming from that, there is no action free at all. This is the typical case where you don't have a good, where you don't have a force moment. And I mean the laws that exist are the following. I don't know, perhaps nature would be the right thing to say, but so if I take here, there's one corresponding points in the stack and the core space, and phi is proper. And when we're leaving core spaces, this one will be separated, so very far proper. But as you all know, properness, when in algebraic geometry, there's multiplied features. But we're talking about a variance of the other is not fulfilled in this semi-algebraic world. But you're used to this being here. You're also used to proper maps satisfying the having the Goethe system. And we also have information. So these are for brain chiefs, and these are for tau chiefs. And finally, so there's some easy notebook structure. So here, so we have our front space here. Where it's done on the column, where we can write this as F5 model. Kind of the fourfold description was that. And then we have a bit more here saying that there exists a core space, even though there's some separation axioms. And the separation axiom in this case is this undimensional. So the inertia is a special part of the diagonal. Properties of the diagonal has to do with separation. So the separation axiom. So we have our three main actors. So we have.
Sorry, can I? What's the action on Z model 2 there?
The switching because it's trivial on the two FI lines, but it switches on. So it's fixed except for the orbit.
Okay, so there's a okay, right.
That's why you have fixed.
Yes.
Except for the orbit. So we have our four spaces. I'm most going to talk about characteristic zero or tame things. These are called tame moduli spaces. Then we will have a good moduli spaces, which are more general. And this will be the mono, of course. Then we come to the ugly piece, and it's the non-reductive GIT or non-reductive with moduli spaces. So this will generalize non-reductive GIT in the sense of virtue when there's a term. But this plus here is to indicate that there is a positive grading of a GM on the unit for the part of a unit of the group acting on some variety. So it turns out that we can weaken this type of event by numbers. But then I also want to put this start actor. So this is the negativo, the kind of really bad one, but it's still quite bad. This has some nice property, and this is good. And let me perhaps say how these roots are held or not held by these various outlaws. So first we have the parents. So for good moduli spaces and also for at least this NR1. People hold that you have to have the finite list of small growth existence. In this case, of the phase change. So again, talk about reaching for various part of homology. Again, we've got so all those kind of shadows of properness actually holds for all the way down here. But then we're getting closer to this one part. Only the that's going to zero, and I don't know more than this. Go of existence is on no, and again it is only. And the idea about this topological model space is that we are getting just the minimum amount of properness to still have some good notion of model space. Whereas these are kind of the more reasonable ones. Having this sometimes enough what defining what this means in more generally, again, it's going to go over here and it's going to be more. And then we also have the characteristic P picture. Let me put that here. These are the adequate spaces. So this is generalizing GIT in, let's say, equality to 0. And this is dealing with GIT in positive. And for this adequate story, we really don't know anything in general. So I'm not even sure if this is the right. It might be that this definition that's in the round and kind of looks reasonable, perhaps it's not the right one. We certainly know nothing about that model space. And the reason is that so in Mori, we have this nice local structure, and that's also different here. Here it's kind of low, and here don't really know how these more general notions looks like. All right, so that means I'll go into some more details. And first, let's see some examples, and let's start with the model analysis. So, I did the definition. This is a good model like this. This is with the deposit path. We go separated, and I also want it to be an adverse space. For one space, it's what the about. And then there's this nice homological characterization of a good model space. It says that it's pushed forward on cross-square sheaves to the center. It's kind of miraculous that just imposing this thing on sheaves is going to give you lots of good properties, in particular this kind of properness-like properties. And then finally, we also require sections to be divided. The basic example is to see what happens when we are at a point with an action of G. When is this a good model space? Then this dogmatic, this kind of matic reasonable group So it's just exactness of taking G invariance of identify by the with taking zero applications, effective basis, and this is exact besides the one we use in your done. And this is the definition of the reductive. So in character zero, just reductive. The input variable is figured. That's the basic example. Next example is affine. So if you have a linearly productive group acting on an affine scheme, then we have a map from A, like E, to the G invariance. So this satisfies condition 3 or 2 or 0. And now the exactness follows from the exactness of G invariance. This is also a good model. The other thing I point out is so let's say G inductive acting from A, well, when we have potential the same story, we have this projected GIT quotient. From the benefit of and here we can immediately also see that the local structure of projected GIT is just affine GIT. So we can look at take a G variance and the assumption, and we are getting the local picture in terms of affine GIT. The local structure here is that the projected GIT quotient is an affine GIT quotient. The risk of in this case, but more generally, it will be just kind of. So verifying that things are good model spaces is kind of done very easily in this case. But conversely, just starting with this abstract definition is not at all clear that it has a direct relation with the objective. So yes, one example. A non-trivial example. I'm going to get to. Is we let G and F with weights plus 1 minus 1. So taking X and Y. And then we have the stack. And it's the moduli space, which is supposed to be the invariance. Variants are just the 0 elements to this side. Just let's say 1. And the picture is that you have the orbits on A2, which are essentially the parabolas, except that at the origin, we have the parabola, but then we also have the x-axis and the y-axis, the x-axis, and the origin. So it's going to give me 3 points. And if I adjust it to the x-axis and the y-axis, I'm going to get a non-separated affine line, and that's a bad. Well, it's not that bad, right? But we are going to also have the origin here, which is going to contribute a big gem. It's a fixed point of that. So this is what's going to make this map being like a problem. If I would not have this, it would be very non-separated, but this is still not separated, but it's getting close to the problem. And especially if you look at over the origin, you see that there are these 2 non-closed orbits. They're locally closed here, opening with either, but then we have this unique closed orbits. So that's kind of the fix to this non-separateness that we say that every pi we should have unique closed points. That's very well known on GIT. We have in every closure of the orbit there's a closed orbit. There's a unique closed orbit in every orbit. Sorry. So let me give you the main properties. So let's start with the topological properties. So there's which is kind of the I don't have it anymore. We see that this is not bijective, but it's close to be bijective in the sense that there's a unique closed point in every pi. So like a polystable object in the pi. So for all that's in the good model phase, it is a unique X naught. Right, which is closed. Well, that's a replacement for bijectivity. And technically, it's not separated from the property, but it turns out that this is a bit universal close. But that's the best you can hope for. And as I already mentioned, it has the property that it's a preserved coherence. So let's say if X is defined as pi, over some entire phase, then first of all, so it's also a good model phase. So if you start with a finite generated K algebra, take a variant with finite generated K algebra, and more generally just from this internal setup, and also this is the same. That's two nice pictures of the model spaces. And then what I so far hasn't mentioned that perhaps people mostly think of in terms when you talk about having a coarse model space. So is that it's the closest approximation of an algebraic space to your stack. So this pi is initial among but it's not a good thing to start out from this and say, well, we have a nice smaller space if it's initial. This puts very weak conditions. When the topology might be quite basic. And we'll see an example later on where you might have a something close approximation. It's even a great space, that's still very, very bad in terms of very far from the and by day. And let me perhaps also mention what I mean by Goethe existence a bit more precise. So, now I can make it precise here. So if we assume that the good model space is complete, so we need those points, then I can look at range leaves on my stack. I can create it to range leaves. So you would do growth existence, you would look at fiber. I'm not going to do the fiber just at x naught. So here the neighborhood. So you need those points for my stack. So this is kind of a even stronger version of the growth existence. And this is going to also kind of give you probability change, which you can write in kind of mimicking this. Let's assume that we are over a semi domain. And we'll take some sheet, and we can ask about sections in topology of my F and compare it to the justice is first. And then finish the further or projection. So this kind of you do propagation to use the this. And again, it's not a full fiber of zero, you just read this first one. So it's really mimicking being proper and bijective. And if it would be bijective, there would just be 1 point. And now I just want single close points, and I'm taking my close point as my fiber. So. And let's perhaps also say something about the little structure. Now we'll go over to the next layer. This is the local structure of and now I'm not assuming that I have a good model space. I'm just starting with an stack with affine down. So in particular, my stabilizer with affine, I'm not allowing, and I can be the right with two curves at my stabilizer. And then I'm picking a point. Those points. Stabilizer. I don't have it, I do not see that they have a good model space, but then there exists this Italian local structure, so there is some affine not some root. And here we have a model space. So it's saying that for any Hilbert stack, it's never have a point with the Hilbert stabilizer if locally, locally, looks like it would have a good model. So you could say that this is locally, it locally looks like a good model. It also, well, that to be more precise, you can make sure that there is a point here. That the X and the paradox. And you can even make this equal to G, at least if you are in practice. Or not very close to it. So but you can actually get this for like G to that in general. And I forgot the numbering now. Let's go to the next factor. So this will be the non-reductive good model phase. So if we now start with a affine like affine JT or affine non-reductive JT and just try to do best. And our quick let to see that things don't work out so well. So well, there are even more bad things happening in dimension one concept. But let's kind of easier to actually think about this context when I translate x by y, or t act by shifting x. So the picture and the following with my plane. If y is bigger than I'm translating well in my GA, but if y is 0, I'm not the GA actually is bigger. So the stack picture it will, when all these lines are just orbits, so I have one orbit per y, except for y equals 0 when I have a full line of orbits here. What this means that here and here I just have a VM, no satellite. This is one y not equal, whereas here I have a fully one of VGA. And now if I would be close to bijective, and all these close points on the affine line should go to different close points in my model space on sort. And if I would try it with invariant ring, which is the closest thing, if you want to have something affine, this is the best one you can hope for. This is just going to be a of y. So now my map here to mapping it to the affine line. This is my attempt for a model case or a model case of sort. But we see here that the fiber or 0 is really bad. And you can also see that the variance jumped quite drastically if I would base change to y equals 0. Then suddenly I get lots of more variance. And out of the variance, I get the whole behavior of the x too. So I'm not getting this Yankee phenomenon where I'm restricting to a closed upright yet, suddenly get more variance. So this is kind of really bad, and not any solver, not any not like force model or anything. That's recent. So let's see what we can do to fix this. And this is kind of like the idea of virtually wrong, false, and parallel. But there are certain non-reductive group actions that are better than others, and one single out the class of these. Positive graded, we are positive graded the total. If it does have uniform group acting, it's not very bad. It can have like infinity energy invariant and so on. But if we combine the GA with also some reductive part, and it has to be in a way that the GA acts not really on GA, it's going to be some other product. I'm essentially going to do the same example as before. But I want to have G act by n minus by x. But now I'm also going to introduce some G on the ring and the GA to make this well behaved. And I'm going to do it in a way that I'm identifying all these red points with 1 point on this. So I'm going to let the GM act with weight 1. On x, but I don't want it to act with 1 on y. Let it act by y0. And for this to make sense, then I have to also put weight 1 on t. So put 1 here in this action. So now what happens is that G. Let's perhaps first look at the picture. I still have the same the green action from the GA. Now I also have the action from the GM, and it's going to act contracting onto the y-axis for every y. And that means that the picture now is that I still have this line as I had before, but now there's a GM stabilizer. The VA collapses to a line, and GMX figure there. And for this red thing I had before, it's going to be just 2 points left. It's going to be the one where I have x not equal to 0, not equal to 0. Here I have VGA, and here I have the order, and I have a VG. So now you see now I have that one. Well, it looks more like a good model phase switch. And might wonder what's so special about this example that makes this work. And then well, you might have different arguments and so on. But it is what, to me, what's kind of really explaining what happens is that the invariance of my ring with respect to the full group, in this case, equals the invariance with respect to the So the invariance with the G is not y, as is the invariance of the group. And we know, for example, that invariance of a ring with the reductive group is always finite. So we can ensure that the reductive part has the same invariant ring and the finite. So what happens in general, So let me call that affine. This will be the first instance of affine on bracket 0 GIT. So I'm going to be those characters 0. This theory is kind of not relevant in conflict characteristic for the following reason. So if I'm starting the level G, and it has a uniform radical, and its potent is reductive, like I mentioned. But what happens in character 0 is that it's always expected. I'm going to call this R. So in character 0, it always kind of looks like a reductive part acting necessarily on some uniform. And now we can ask for to say that this or another serial guarantee the environment of with respect to our G acting environments with respect to the full group, which are for a smaller conductive. And so this, for example, settles the question of having a finite generated invariance, but it also kind of fixes this problem that there are more invariants when it comes to a closed subscheme. So that's what I call an argument that we have. If we ask to the importance, we now have a problem here, and we have to know that it's exactly the invariance, and this might be a bidirectional. So this is the output here is that whenever I have an action where the invariance with respect to the whole group equals the invariance with respect to reductive, then we have kind of the usual problems of GIT more or less. We perhaps add here, let's say MRA GIT, then I'm requiring a bit more. So I'm not just asking about invariance of A, but I'm adding kind of the regular representation here of U, and I'm adding it even A times. I want this to be and the situation of Berkeley they assume that there exists one only subgroup which acts with strictly positive weights on the Rydh algebra of U and with semi-positive weights on the ring. And if I do that, then this is going to imply this. Because here now this is going to have strictly positive weights except for K itself. So if I do the G invariance here, this has semi-positive weights, this has strictly positive weights except for the K, and I will get this, and then I can also show that using the other knowledge that you have to get also on level A.
So does that apply for all A?
Yes. So this is what I call NR plus. This this thing and this implies. So the closer we get to having good knowledge. But I mean, as I said that even for LR1, all kinds of good statements solved. But not for LR0. Okay, I already mentioned that in principle, everything that's good about good knowledge bases is growth existence, phase change, local structure, it all has an analog for at least NR1 good knowledge base. Let's go to the topological thing. Well, I have given a definition of the non-reductive. The knowledge basis, it's it's let me pass this out to be honest. So, this is one of these non-reductive knowledge bases. And as before, we will come not too crazy, and we will read that also with the right functions. But then we're going to replace this exactness with instead we are saying that for the structure sheet to functions. We saw that in F9 NR0 GNT, this holds from this equality. It's not quite clear this implies that if in that case R invariance equals G invariance, but actually does, then one also need to also say after range from X. And then there's unfortunately one has to add a little epsilon here, but it's essentially enforcing that we have a non-reductive space. So this is an NR0, and then we also need NRA, which will also kind of say that the polynomial algebra is able in the sense that we can make it precise. So the conormal algebra is an algebra over BG, where G is satellite point. So you can think of it as a G representation, and then you have the same condition of this. So this is a pointwise condition on X, very similar to saying that you have linear reductive stabilizing point points. So this is saying that the stabilizing points are sufficiently good. The action is sufficiently good, and it's also the action on its pattern base essentially is also good. So like the definition of the complexity model space and this is going to be minimal things that capture all these examples. It's essentially going to require this that there exists a unique closed point in fibers. Plus that the map is closed. Let me perhaps write this up. So phi relatively closed. Unfortunately, this is not quite enough, which has to do with this like propagation theorem. It has to do with child neighborhoods, and when you're doing child neighborhoods, you have to do with finite covers. So we also require that one holds for any finite map. So if like this. The for this x prime where there's finite and this is the sign factorization. So I mean, in this case, due to being universally closed, this composition is universally closed, and you can prove that this is finite. So here, and there was a motivation. I mean, why would you care about this topological model spaces? Well, it's simply because we don't have enough tools in a non-reductive setting some things have apparently non-reductive has been done without more topological arguments, which also hold to the topological model spaces. So many of the proofs are based on just having these properties. So let me perhaps say that we have if we have a topological model space, then we have this what I wrote before, the finiteness rules. We have these topological properties that are held by definition, and but also this universal. And also, one can prove that also that finite holds. And then my corollary is very nice that model space, sorry, good model space is not about the model space with linear vector. So this is capturing the part of being nice and effectively to being proper and having right fibers. And the only thing that's missing from good is having that status. And there's similarly also, one can see that it's A good model spaces are similar being topological model spaces plus this the A good or A is at least 2. A few more minutes. Let's go to the goal of the movie and also the talk. So I guess that's the goal. So even though this is the kind of the theory of good model spaces was something nice in that it captured what happens in GIP. With these other methods, it did not really give new examples. But recently, seeing a published blog here, so if X, say that X has finite height in the field, we have my diagonal, then we sit that good model S, and on here, first we should have linear graphic parameters at both points. Now that this is necessary, but then we have to somehow control that it has a couple of the model base, that it has the right thing. And what they did was to use the notion of interactivity. So say active, productive. So it's all the kind of separation axiom in terms of like dilation rings, but a bit more complicated. And finally, we need that X unfunctional. The analog of the model basis. Unfortunately, it's not quite true if no if statement, but very close. Let's see if I want affine diagonal. No, let's do that. So this is an if statement that this holds for all the non-reductive good model spaces starting with A equals 1 or 2. So A should be actually locally wonderful. By which I mean that it should exist from tell neighborhood and have local structure where there does exist of the models. And they should again map a point for close some point that could exist map where there does exist a couple of models. This is clearly necessary, and we can thank the bottom point. Secondly, we want to place this peak reductive bar and like it is and completes. I have 1 more minute, so I don't. Okay, let me stop there.
What's the difference between N complete and S complete?
Yeah, that would take more than 1 minute, 2 minutes, I think. I'm not going to use an overall, but that's very anyway. So there's a illustration saying when points are going to be in the same fiber. So we say that X is a nearby specialization. If Y is the specification of X and some where X is and X is A1. But we do this example like an A2 moduli and so on, we have several K points that specialize. So we say that there are nearby specification if they are specialized as K points. And then we can define this as the closure under this illustration. But this is going to be in the case of if the model case, this is just separating fibers and putting everything that's in the same path. But this is the way of defining without having everything in place. And then now n completes. So first that exists a post or exists unique both points in every element of the graph. It's that if I'm starting with a closed subset, then it is obviously true for implies inverse equals to theta reductive is a way of verifying this using this specific A1 moduli and relationals. But it's the same thing that happens in definition of logical multipliers. You have to go to finance. But this is what actually makes this difficult to verify without having finite criteria. Okay.